طيب تمام، خلينا نبلش. بنشوف إذا في عندكم أي أسئلة أي استفسارات. Any question على اللي حكيناه المرة الماضية؟ إذا عندك أسئلة. تمام. Okay, so let's continue in what we started last time. Last time we started chapter 5, which is an important chapter which covers the other type of digital logic circuits that you usually find in digital systems, which is the sequential circuits, and more specifically the synchronous sequential logic. So we started last time in the introduction. We covered what is meant by a sequential circuit and what is the difference between it and the combinational logic circuits that we covered in chapter 4, and what are the different types of the sequential logic circuits. So basically, we said the combinational logic circuits. We covered already the chapter 4, and what makes these circuits different from other types of circuit is basically the outputs in such circuits are only dependent on the current input value, and we discussed that in detail. Then we said we talked about an example to design a counter, and when we discussed the design of that counter, we discovered that in order to design a circuit that can count from 0 to 9, we cannot do that using a combinational circuit only. We need another component to add to the combinational logic circuit, which is basically, we said, kind of memory to store the count value in order to know what is the next count. So this is basically a sequential circuit, which is a combinational logic circuit that has a memory that can store some value that indicates something, that tells something about the state of the circuit. That's why we call the stored value, we said last time, the state, or technically the present state, the current value that is stored in the circuit. So basically, this is the sequential circuit. It is a combinational circuit along with some storage or some memory. There are two types, we said, of sequential circuits, the asynchronous type and the synchronous type. And chapter 5 technically is concerned with the synchronous sequential circuits. So we said the combinational or the sequential circuit is a combinational logic circuit where we have certain number of inputs, certain number of outputs. In addition to this component, we have some storage or some memory that can store some value that tells us something about the state of the circuit. Now, what makes these circuits different, the sequential circuits different from the combinational circuit, is the fact that the outputs are not only function of the input, they are also function of the present state or the current value that is stored in the circuit. This is very clear if you go back to the counter example, where we said we need to store the current count value, which we have to take or which we have to know in order to increment, to process it by incrementing it to get the new count value, which is our output. Now, one more thing here is that the circuit has also, or should be able also, to change the stored value, and this is also done by the combinational logic component of the sequential circuit. So the combinational part of the sequential circuit does not only compute the output, it also calculates the new value to be stored in the memory, and this new value we call the next state. The value that is currently stored in the circuit is called the present state, or Q, and the next Q of t. And the value to be stored in the memory is called the next state, or the new value, and we call it Q of t plus 1. And we said this notation is basically to reflect the dependence on time. T implies now, t plus 1 implies the next, or the value in the future, the next value, the value to be. So So this is the main difference. These are the main differences between sequential and combinational circuits. Now, however, we said that the sequential circuits are of two types, the asynchronous type and the synchronous type. And the main difference between these two types of sequential circuits is basically the timing, or basically when do we allow the new value to appear or to be stored in the available memory or in the available storage. And in asynchronous sequential circuit, the next state or the new value is allowed to be stored, is allowed to go into the memory element or the storage as soon as the input changes. That's why it is asynchronous. It is not tied with time. It is not synchronized with time. So this is what is written here. The stored value or the state is allowed to change at any instance of time. Now, this type of sequential circuits is not of interest in this course. It is usually taught in advanced courses, as we said last time. But I want you always to remember this diagram, that we have inputs, we have outputs in such circuits, similar to the combinational circuits we covered earlier. And at the same time, the combinational circuit does not only take the external inputs as inputs, it also takes the stored value or the present state to output not only the observed outputs or the outputs that we see as users, but also to compute or calculate the next state or the new value to be stored in memory. And this is very important. And we will talk about it a lot in the coming few lectures. Now, the other type of the sequential circuits is the synchronous sequential circuit, and nothing new here. We have storage elements, we have combinational components, we have inputs, we have present state, we have outputs, the same thing. The outputs are function of not only the input, the external input, but also the present state, the value that is stored in the storage elements or in the memory elements. So what is the difference between the synchronous sequential circuits and the asynchronous? Basically the timing, as we said. When do we allow the next state to be stored inside the memory? For the asynchronous type, we said there is no timing. As soon as the input changes, the next state is stored into the memory. However, in the synchronous component, synchronous implied it is synchronized with time. So basically, we need to allow the next or the new value to be stored in the memory element or in the memory or in the storage element during some time or at specific time. So that's why we need another input to the storage elements, which is clock, some signal or some input that is related to time, that we can use to as a time reference to decide when to allow the next value or the next state to be stored into the memory. And this will become very clear as we go on. But as I said, keep this figure in your mind, its different components and attributes, and keep this basic understanding. Synchronous sequential circuits are basically combinational logic circuit plus memory elements. These memory elements, they are also controlled by some time signal, which we use to decide when to store a new value. In the asynchronous type, there is no clock, there is no timing. We allow the new value to be stored as soon as the input is the input changes. Okay, so this is what we covered last time, technically. And I usually spend some time on this because I want you to grasp this concept. Because if you get the idea, the rest of the chapter is very straightforward. Okay, so there is a new factor that comes into action here, which is time. we need to understand, need to understand this concept, the timing of operation. When we talked about combinational circuits, we did not talk about time at all. However, in sequential circuits, there is time, especially in synchronous sequential circuits. We want to know when we can store the value or update or change the stored value. And this is basically the rule of time in synchronous sequential circuits. Okay, so this is what we covered last time. Let's move now to the next topic, which is the storage elements, or basically the memory. So in order to build a sequential circuit, we need combinational component and we need memory, or we need storage components. So the combinational component, we already know it. We are professional in working with combinational logic circuits from chapter 3 and chapter 4. However, in order to build the sequential circuit, we need to have a memory or some storage device. So this, the coming few slides are about this topic, which is what are the storage elements that are available that we can use to store the state of the circuit, or the present state of the circuit. So a storage element basically is a logic circuit. We will see shortly that a storage element is nothing more than a logic circuit that can store 1 bit. So each storage element can store 1 bit. So if you want to store more than 1 bit, you need to bring, or you need to use more than 1 storage element. Now this ability to store the bits is valid as long as the power is supplied to the storage element. So as long as you give power to the storage element, it is capable of remembering or saving or storing this bit or these bits, depending on the number of storage elements. Now, there are many types of storage elements, and however, they all have certain number of inputs and output. Now, the inputs are basically used to specify how to control the stored value, what to do with the stored value, whether you want to store a 1, you want to store a 0, you want to perform different actions on the stored value. This is basically performed using certain number of inputs, and the number of inputs vary from one storage element to another, as we will see shortly. Some storage elements, they only have 2 inputs, some of them they have 3 inputs, and so on. So basically, any storage element has a set of inputs through which we can specify how and when to change the stored value. So using these inputs, we can say store a 1, store a 0, complement the stored value, and so on. Okay, and also some of these inputs, depending on the type of the storage element, can be used to specify when the inputs can affect the stored value. For example, you want to change the stored value to 1. However, you want this to happen at certain instant of time. You don't want to happen now. So usually you will have, in this case, another input to control when to allow the inputs to affect the outputs. Okay, so this is for the inputs. Now for the outputs of the storage element, because it is a logic circuit, as we said, basically the output is Q, is called the Q, which is basically the stored value. It is the stored value. The output is basically the stored value. And by definition, most storage elements, they have with they come with another output, which is basically the complement of the stored value. So Q is basically the stored value. Q bar is the complement of it. So the commercial storage elements, they usually come in this shape, where you have 2 outputs, one for the Q and the other is basically the complement of the stored value. Okay, because this is helpful when you build the circuit, because sometimes you want Q, sometimes you want Q bar, as we will see when it comes to designing sequential circuits. So instead of bringing an inverter to complement Q, it is already included inside the the circuit itself that represents the storage element. So this is very important regarding the storage elements. What is inside this box is basically a logic circuit that is capable of storing 1 bit. It has certain number of inputs to control the stored value, how to change the stored value, and when to change the stored value. And basically there is the output Q, which is the stored value, and its complement is also another output Q bar. So if you look at different types of storage elements, you will see that depending on the type of the storage element, there are basically 4 types of operations that you can perform using the inputs of the storage element. Basically, you can use these inputs to change the stored value to 1, which what we call a set operation. So when I say set the value, it implies change it to 1. Another operation that can be implemented or supported by the inputs is to change the stored value to 0, which we call it a reset operation. So when I say reset the stored value, this implies change it to 0. Also, depending on the type of the storage element, the operation specified by the inputs could be no change. In other words, keep the stored value as is, or we call it hold. Don't change the value. And lastly, some storage elements, they come with this operations. They support this operation, which is complement the stored value, or we call it toggle operation. All right. So these are different types of operations that can be performed by the inputs of the storage element, depending on the type of the storage element. Not all storage elements support all these operations. Some of them, they support all. Some of them, they support subset of these operations. Now, if you look at the storage elements, they can be classified into 3 different types. The first type is called latches. The second type is called the clocked latches, and the third type is basically called the flip-flop. But at the end of the day, all of them, they are basically logic circuits. They can store 1 bit. And what is the difference? Basically is the timing. When these storage elements respond to the change in the input in order to change, to affect or change the stored value, as we will see. So we will discuss these 3 types. However, our focus in this chapter, when it comes to the analysis and the design of a sequential circuit, is concerned with the third type of flip-flops, of storage element, which is the flip-flops. So why do we discuss the latches and the clocked latches? In order to know what is flip-flops, we need to know what is latches and what is a clocked or controlled. This is clocked/clocked. It has to be clocked/controlled. They call them clocked latches or controlled latches. So today and on Wednesday, our discussion will be only on storage elements. What are these storage elements and how do they work and how to analyze them? Okay. Any question? So we have covered nothing difficult so far. We just went over what is meant by sequential circuit, and we defined what is meant by storage elements and the different operations that can be performed in storage elements and the types of the storage elements briefly. So let's start with the latches as storage elements. So there are many types of latches. Okay, one example on latches is basically what is called SR latch. SR latch, or they call it the cross-coupled NOR gates. Cross-coupled NOR gates. Basically, the logic diagram of this circuit is consists of 2 gates, and specifically 2 NOR gates. So we have, for these 2 NOR gates, we have basically 4 inputs. 2 of these inputs are connected to external inputs, which we call them S and R, which are the short or abbreviation for set and reset. Abbreviation for set and reset. Now, 2 NOR gates implies 4 inputs. So 2 of them are used for external inputs. How about the other 2 inputs? If you look at the circuit, we see that the second input of the bottom NOR gate is basically connected connected with the stored value Q. Basically, it is taken from the output back to the input. The same thing, the second input of the top NOR gate is taken from the complement of the stored value back into the input. And this is something we have never seen when we talked about the combinational circuit. In combinational circuits, we always saw that the data or the information flows from left to right or from inputs to outputs. However, in this storage element, we see that information also flows in the backward direction from output to input, from Q to R. And this is basically how the circuit remembers. Because if you want to remember something, you need to repeat it. You need to go back in your memory and remember it. So this is how the circuit remembers. It takes the value back and use it as an input. Okay, so this is basically a circuit that can store 1 bit, which is stored here as a Q, and you can manipulate this Q based on S and R. You can force it to 1, you can force it to 0, you can hold it, and so on. Okay, so let's try to analyze this circuit. This is very simple circuit. This is the box that we saw on the previous slide. So inside this box, this is called a storage element, and technically it is called an SR latch, an SR latch. Let's try to analyze this circuit by changing S and R and see what happens to Q. Okay, so let's, and how will we do that? We will do that over time. We will start by saying let S equals 0, R equals 0, and the stored value initially be 0. What will happen if we set S and R to 0, 0? What will happen if we set S and R to 1, 0, and so on? So basically, this is what we have. We have here Q, which is the initial or the observed value, which is the stored value, and we will assume that initially its value is 0, 0. Now, what will happen if I set S to 0 and R to 0? Basically, I'm asking you to find out what is the new value of Q, which is I will call Q plus, or Q of t plus 1. It is written here. Q is Q of t, which is the current value that is stored in the storage element. And the Q plus, for short, and just to make the table compact, is basically Q of t plus 1, which is the value that will appear or that will be stored. Okay, that will be stored. So initially, I assume that the value that is stored here is 0, which means that Q is 0, and I am asking what is the value that what is the new value that will appear on Q. So Q plus is not a new output; it is the new value that will appear on Q when I change the input. So now I force the input to 0, 0. Now if Q is 0, what will happen? What will be the new value for Q? So Q plus is the new value for Q. It is not a different output. Okay, how can we do that? Basically, it is analysis. You need to analyze. So let's look at everything is on the slides. So now we set S and R to 0, 0, and Q is 0, which implies that Q bar is 1. Now, if I tell you this is the current situation, what is the value, the new value for Q? Now, to analyze this, we can say, let's take this NOR gate. If we take this NOR gate, the inputs to this NOR gate is basically 0, 0. 0 or 0 is 0, complement 1. So Q bar is still 1, and 1, if you take it back here, 1 or 0 is 1, complement is 0. And this thing continues to happen as long as SR is fixed to 0, 0. So technically, what happened to Q when I set S and R to 0, 0? What happened?
It stayed the same.
It stayed the same. مظبوط؟ لأنه أنا أخذت 0 0 or 0 complement 1 1 or 0 complement يطلع 0. Keep doing that, it will stay the same. So what happened to Q? Q will become 0 and Q bar will become 1, which is straightforward, which implies that the value to be stored is basically the same as the previous value. So nothing has changed. So if I want to hold, if you remember, we call this operation hold. If I want to hold the value in the SR latch, I need to make R and S 0, 0. Okay? So, so now what if we change the, if we assume that the initial value Q is 1 and we set the inputs to 0, 0, what is the new value? How this will affect Q? What is the value of Q if we do that? The same thing, we can analyze it in the same way. We say here we have 0 and 1 is taking this gate. So 1 or 0 is 1 complement 0, so which is this. 0 or 0, 0 complement. So if you take this 0, 0 or 0, 0 complement 1. So nothing has happened to Q and the Q bar. So again, Q plus or Q of t plus 1, or the new value that will appear on Q, is basically the same old value, the same old value. So this is basically implies that as long as we keep S and R 0, 0, then whether Q is 0 or Q is 1, it will stay the same as long as S and R are 0, 0. This operation we called, if you remember, is what? The hold operation. So this operation, which is the new value, is basically the old value, can be achieved in the SR latch as long as the S and R are kept 0, are made 0. So if Q is 0, it will stay 0. If Q is 1, it will stay 1. Okay, so this is the first scenario in which we set S and R 0, 0. So we have two external inputs that we can use as users. So how many combinations we can have for two inputs? 4. 0, 0, 0, 1, 1, 0, and 1, 1. So here we covered the first scenario where we forced S and R to be 0, 0. The next scenario is when S and R are 0, 1. What happens if S is 0 and R is 1? So we need to study two cases, when Q is 0 and when Q is 1. So the first case is when S is 0, R is 0, and R is 1, and Q is 0. What will happen? The same thing. We can analyze the circuit. This is 1. Here we have 1, and with this 1 or 1 is 1 complement 0. 0 with 0 complement will become 1. So nothing has changed. So the old Q is 0 and the new Q will be 0 also. And if you look at the circuit, Q bar is basically 1. So nothing has changed. But does this imply that also the scenario when S is 0 and R is 1 implies a hold state? We cannot decide until we see the next case, which is when the Q is 1. So if initially, or if the stored value is 1, and we set R to 1 and S to 0, what will happen to Q? Let's try. 1 or 0, 1 complement 0. Okay. And then 0 or 1, 1 complement 0. So this will be changed to 0. Initially, when we analyzed it, it gives 0. But when we go backwards, also, it will become 0. So 0 now goes here, 0 or 0, 0 or 0, 0 complement, this will become 1. So this is very important. Let's do it again. I started from here. I said, let's take this one here, 1 or 0, 1 complement 0. So nothing has changed. But if we take this back, 1 or 0 now, it is 1 complement. So now this becomes 0. This becomes 0. So if you, as I said previously, this keeps happening. So now I take this 0, 0 or 0, 0 complement, this becomes 1. Now repeat this, 1 or 1, 1 complement, this becomes 0. So we reached a stable state. We reached a stable state. So initially there was, the initial state was different than the state that we reached at the end. So what will happen here is that Q will become 0 and Q bar will become 1. So regardless of the initial state, whether it is 0 or 1, as long as S and R are 0, 1, what is the next state? Or what is the new value? It is 0. So always Q plus, or the new value that will appear on a Q, is basically 0 if we set S to 0, if we make S 0 and if we make R 1. So this operation, we mentioned it previously, it is a reset operation where we force the stored value, which is a Q, to become 0, 0, to become 0, 0. So as this is a summary here, as long as S and R are 0, 1, then Q plus is always 0, which implies it is a reset operation. So here we have a reset operation, here we have a hold operation that we can perform on the stored value. Any question? It is kind of confusing at the beginning, but it is not that difficult to go through. Try to analyze these circuits for different input combinations and different initial stored value, which is a Q, to figure out what is the effect of the input value on the stored value. Okay, so the third case now here is basically when S and R are 1 and 0 for different values of Q. So if the initial value is 0 and we make R 0 and S 1, what is the new value for Q? Let's take it 0 or 1, 1 complement, this will be 0, 0 or 0 or 0, it is 0 complement 1. If you take this back, you will see that you reached a stable, a steady state value or a stable value. 1 or 1, 1 complement 0, 0 or 0 complement 1. So this will keep repeating. So we reach some steady value, which is Q equals 1 and Q bar is 0. So basically what happens here, Q becomes 1 and Q bar becomes 0 if you do the analysis. So Q plus or Q of t plus 1, or the new value that will appear on Q, is 1. The same thing if you try the combination when S is 1, R is 0, and the initial stored value is 1. If you try to analyze it, you figure out that Q plus, or the new value, is basically a 1. So this will become basically what? A set operation. So here we have a hold operation, here we have a reset operation, and here we have a set operation. And this is achieved by specifying the values of S and R. All right? So this type of storage element, which is a latch, allows us to perform set operation, hold operation, and reset operation. Okay, now the fourth scenario, or the fourth possible input combination is 1, 1, when R is 1 and S is 1, and this is very important here. And let's start by assuming that Q is 0. The initial stored value is 0. The initial stored value is 0. So if you try to analyze it, 0 or 1 is 1, complement is what? 0, right? So the Q bar becomes 0. If you take this 0 back here, 0 or 1 is 1, complement 0. And if you keep repeating this, you will end up with the same, where both Q is 0 and Q bar is also 0. Q bar is also 0. If you try the same combination also, the same input combination with Q equals 1, 1 or 1 is 1, complement 0, 0 or 1, 1, complement 0. So what's the problem here? Or what is this operation what is this operation? If you look at Q plus only, you can see it is similar to what we had here, that we are forcing the stored value to be 0 when S and R are both 1s, similar to this case. However, there is a problem here. What is this problem? Can we call this operation here a reset operation? If we look at Q plus only, or the value that is going to appear on Q, yes, it is a reset. But if we take into consideration Q, the complement of the stored value, there is a problem. How come is both the value and its complement are zeros? And this is written here. The new value or the next value is basically the complement of the old value. But there is a problem here, which is that by definition, a Q bar, this Q bar is the complement of this. How come the complement and its original value are the same? So this is a problem, because we defined the Q bar to be the complement of Q. And this is trivial. So this is the case where this input combination is basically not allowed. You cannot use it. You cannot use it when you use the SR latch. You can't use this input combination because there is a contradiction. Both the stored value and its complement are 0, 0. However, using this latch, you can perform a hold operation, you can perform a reset operation, you can perform a set operation, and this input combination, which is S equals R equals 1, when both S and R are 1, this is not valid input combination. You cannot input this value because it gives you some undefined state where both the value and the complement are zeros, are both zeros. Okay? So what we have here, basically, this is a summary. We have a storage element which is called SR latch, or cross-coupled NOR gates. Two NOR gates that are cross-coupled. They are connected this way. This is basically, we will use it as a block. We'll use it as a block where we have two inputs, S and R, which can be used to control the stored value, Q, and its complement. And its complement according to the table below. When S and R are 0, 0, we said that this is a hold operation or no change. Hold operation, no change. What does it mean? It means that the new value is basically the old value. This is the meaning of no change or hold. The new value is basically the old value. When the input is 0, 1, what will happen to Q? In other words, what is the new value? Basically, it is always 0, which is a reset operation. So whenever S and R are 0, 1, are forced to 0, 1, then the stored value will be changed to 0 regardless of the old value, whether it is 0 or 1. And this is we already saw on the previous slides. The same thing, the third case, when S and R are 1, 0, the stored value will be changed to 1 regardless of the initial value. So this is the set operation. And the last state, which we called it the invalid state or the invalid operation or not allowed operation, where when the S and R are both 1s, when the S and R are both 1s. Okay, so very straightforward. As we said, we can store 1 bit here in a queue. We can change it, manipulate it by S and R according to these values, to achieve these different types of operations. So if you look at this storage element, it only supports 3 types of operations: no change, reset, and set. There is no toggle or there is no complement operation. Okay. Now, if I ask you this question, we said that these inputs are used to specify or are used to modify the stored value, and also they are used to specify when the stored value can be changed, right? If you go back to the definition of the latch or of the storage element, we said that the inputs are used to do 2 things usually: to specify how to change the stored value and to specify when to change the stored value. So if I ask you here, when does this storage element changes the stored value Q in order to be the new value? Did I look at time when I analyzed the SR latch circuit? Did I look at time? Did I care about time? Like when I said S is 0, R is 0, what is the new value of Q? I simply analyzed the values, the path, different paths, and figured out the new value of Q, which I called it Q of T plus 1, right? Or the new value of Q. So this new value, this new value, which is calculated here and here, appears on Q as soon as I change the input. So is there time related to the operation of this latch? فعليا زي ما حكى جمان, no. There is no time. As soon as the input changes, the value that appears on Q, it changes to this, or to this, or to this, depending on S and R. So this is very important. The stored value in latches in general, not only the SR latch, the latches in general, which is the first type of storage element that we are talking about, the latches in general, basically they allow the stored value to change to the new value as soon as the input changes. There is no connection with time. There is no relation to time. Okay, so they allow the stored value to change at any instant of time. And this is very important. Keep this in your mind. Latches, they allow the stored value to change at any time, given that the input changed. Okay, given that the input changed in a way that affects the stored value. Okay. And this is only one example on the latches, which is the SR latch. There are other types of latches, but what we are concerned of is the concept of latch. Latch, a storage element that can allow the stored value to change as soon as the input it changes, if that change affects the stored value. Okay, here is an example, and it introduces a new concept. Basically, it is very similar to what we did on the previous slides when we analyzed the SR latch. However, here we use a different approach to analyze the circuit, which is basically we call the timing diagram. The timing diagram, in which basically we study the effect of changing the inputs S and R on the stored value over time. So basically, this is time. Sorry. So this is time. The horizontal axis is T, time. So we study what happens to Q if we change S and R. So we can represent the table that we had earlier when we analyzed the circuit using this approach. We call it the timing diagram. So it shows the behavior of the circuit over time using this diagram instead of using a table. So if we look here, we have an SR latch that we want to study what happens to the stored value Q when we change S and R, given that we know the behavior of the latch, or how does the latch work, how the latch operates. So we know that S0, R0 means hold or no change, 0, 1 implies reset, and so on. So when we analyze the circuit at any instant of time, we look at S, at R, and to determine Q based on this. So this timing diagram shows us this graphically. So here initially we have both S and R are zeros and Q is 0. When S and R are zeros, then Q is, the new Q is the same as the old Q. So that's why as long as S and R are zeros, the Q is fixed to 0 because it is the same value for the previous time instant. Okay, so if you take a line here at any instant of time, we have 0, S0, R0. So Q now is basically the previous Q, the old Q. The new Q now here is basically the old Q, which is the value before this line. So that's why, since S and R are zeros, the Q stays the same, which is 0. Okay, assuming that Q at minus infinity, time equals minus infinity, is basically 0, or the initial value of Q is 0. So as long as S at any instant of time, if you take a vertical line at this time t, let's say 1, then what is the value of a Q at this time depends on S and R. Since S and R are zeros, then a Q is basically the previous value before this instant of time, which is 0. Okay, the same thing now goes on and on for this instant of time. At this instant of time, basically S is changed to 1 and R is 0. So what is meant by S1 and R0? What will happen to the stored value? The Q will be set. So as soon as this input changed, what happened to Q? The Q changed to set. It changed to 1. The Q changed to 1. Okay, so this is very straightforward. I changed S to 1, R to 0. So what is the effect on the stored value? Basically, it is set. So it is set to 1 at this instant of time. What happens next? What happens next is basically S stayed 1 for a certain period of time and R stayed 0. So for this whole period, basically the operation that is performed is a set operation. Now at this instant of time, S is forced to 0, is changed to 0, and R is still 0. What is the value of a Q as long as S is 0 and R is 0? As long as S 0 and R is 0, what will happen to Q? S0, R0 implies that hold. So at any instant of time during this period where S and R are zeros, basically Q, the new value of Q is basically the value before this instant, which is 1, because we have a hold operation. So that's why if you look here Q was set. In this period, the Q is hold. So we hold it because both S and R are fixed to 0 and 1. Now, next, what happens here? S is 0. S is 0 and R is set to 1. This implies reset operation. This implies that starting from this instant of time, and regardless of the previous value of Q, I don't need to look back in time and see what is the previous value of Q because it is a reset operation. Q is forced to 0. Q now is forced to 0 because it is a reset operation. Then we have 0, 0 here for S and R, which is what? Hold, right? It is hold operation. So from this instant of time up to this instant of time where there is no change in S and R, and both S and R are zeros, then Q is held. Q is not changed. So I need to know what is the previous value of Q before this instant of time, which is 0. So Q stays 0 here. Q stays 0, and so on. So basically, this is one approach to represent or to show or to see what happens to the stored value or to the state. We call the stored value the state when we change the inputs based on certain pattern. All what we need to do is basically to know what is the value of the inputs and how do they affect the stored value at every instant of time, at every instant of time. And we will use this frequently in this chapter because, as we said, sequential logic circuits, they have a new factor into action, which is time. So we need to study the behavior of the circuit over time. Now, before we go, I want just to stress on this. Like, as I said, what makes latches a separate group or a special type of storage elements is basically that all latches allow the stored value to change as soon as the input changes without any connection, without any synchronization with external time or with some timing signal. So if you look here, as soon as S has changed from 0 to 1, the output or the stored value has changed as well. So nothing prevented, there is nothing that has prevented the change in S to affect Q. There is no time. Now, as we will see next time, for other types of storage elements, even if the inputs change, this does not imply that the stored value has to change because we need to wait for certain time to come in order to allow the input to affect the output. Okay, so this is what makes the difference between different types of storage elements, latches, clocked latches, and flip-flops is basically when the stored value is affected by the external inputs. In the latches, this happens immediately. Theoretically, of course, I don't want to go into details, but as soon as the input changes, the stored value can be affected by the change that occurred in the inputs. All right. So this is one type of latches. We will not cover other types of latches in details, but the idea is simple. If you go to other types of latches, for example, here we have another type of latch. I will not detail it. It is called S-bar, R-bar latch. So basically it is constructed, instead of using NOR gates, it's constructed using NAND gates, and they are cross-coupled. The same idea. We have two inputs, set input, R input, and now the set is at the top, the R at the bottom. So if you try at home to analyze it, if you try to analyze this circuit later, the same way we did for the SR latch, you will come up with this table. Basically, 1, 1 for S and R implies no change, 1, 0 implies reset, 0, 1 implies set, okay? And 0, 0 is the not allowed input or the invalid state or the invalid operation, because both the stored value and its complement will be the same. And in this case, both will be 1. In the SR latch, they were both zeros. So technically, what is the difference here? Technically is basically both S and R are now active low inputs. What is meant by active low inputs? They have effect if their value is 0. If you look here, when S is 0, it is a set operation. When R is 0, it is a reset operation. So this is an active low input. So that's why it is called the S bar R bar latch. So it is active low input. So this is available for you. You can build it, you can buy it. So, but you need to be careful that its operation, the supported operations are the same, but the way to control this operation is just the opposite. So it is active low. It implies that when S and R are zeros, they have effect on the stored value. When you compare this table to the SR latch table, it is just the opposite. So that's why we have bubbles here to indicate that these inputs are active low. They have effect when S is 0, which makes Q is 1. When R is 0 and S is 1, it makes Q 0, and so on. 1, 1 is 1. Okay, so this is just another example on the latches. Try to analyze it at home by saying, okay, let's start by Q equals 0, S equals 1, R equals 0. What will happen to Q? What is the new value of Q? Let's try it. 0 and 0 is 0. Complement is 1. 1 and 1 is what? 1. Complement 0. Complement 0. So nothing changed regarding Q. So is it a reset operation or is it a hold operation? We can't tell unless we analyze the case when Q is 1, S is 1, R is 0. So what happens here? 1 and 0 is 0, complement 1. 1 and 1 is 1, complement 0. 0 and 0, 0, complement 1. So what happens when S is 1 and R is 0? Basically, always a Q becomes 0, whether it was 1 or it was a 0. So basically, it is a reset operation. It is a reset operation. So it is very simple, but at the same time important. You need to remember always that there is only one output. There is only one stored value in the storage element. It is a Q. Some people or some students, they keep thinking that, or they keep asking, where is the output for Q of t plus 1? There is no output for Q of t plus 1. Q of t plus 1 is not a different output. It is the same output. There's only one output, Q. If you want to ignore Q bar, there is only one Q. But where is Q of t plus 1? It is not a separate output. It is the value to be. It is the value that will appear on Q when I change the input. This is very important. As I said, some students, they keep asking until the end of the chapter, where is Q of t plus 1? You cannot see it here, Q of t plus 1, because it is basically what is being calculated here inside the gates, and that will appear on Q later. Okay, so I only have Q, which is the value that is stored now. Okay, where is the value Q of t plus 1, or the value to be stored? It is being calculated here, and then it will appear here in 0 time. This is theoretically, but in practice, calculating the value here and then forcing it to the output will take very small amount of time. But we will not go into the details. So basically, I want you to remember this. There is only one Q, and the Q of t plus 1 is calculated here, which is the same way we analyzed the circuit, and it will appear on a Q shortly, or after very little amount of time. Okay? Any questions? Is it clear? I assume that you understood everything if you don't ask, or if you don't give me a feedback. Now, for the invalid case, Sarah, we can't say it never happens. We control it as users. We control it because S and R are controlled by us. So whenever we use the SR latch, we always try not to input 1, 1. Now, if you input 1, 1, there is no problem. Q will become 0 and Q bar will become 0, for example. But this will affect the operation of your circuit if you are using this latch in a bigger circuit. Okay, so whenever we use the SR latch, we always try to avoid inputting 1, 1. All right. Other questions? تمام. So please, أنا بعرف إني I promised to post the slides, but I'm still working on them. But probably by tomorrow night I will finish them. I'll have them posted on e-learning. But you can go through the available set of slides for chapter 5 on e-learning. It's not detailed as those that I'm using now in the lecture, but still you can look at them in order to study for the material that we have discussed so far. Or you can go through the video. Definitely that will be uploaded shortly on YouTube. All right, so next time we will continue. We'll cover a new type or the other types of storage elements, which are the clocked latches and the flip-flops. All right, تمام. يعطيكم العافية.